This video is about nested quantifiers. Nested quantifier is nothing but having multiple variables inside a predicate, one after the other. And this simple concept of putting multiple variables is extremely powerful and can describe some really complicated mathematics. So let me give you a concrete example. Continuity. You all must have done some kind of calculus course. And you see the definition of continuity as drawing a graph and there's no gap in the graph, or you don't have to lift the pencil or so on. But the rigorous definition of continuity in mathematics actually uses predicate logic and multiple quantifiers. So this is how it's defined. We need lots of variables. So we have x, y, epsilon, delta. These are all reals. So their domain is real numbers. And we have a function f from real numbers to real numbers. Then we say f is continuous at x if for all y, for all epsilon, there exists a delta such that x minus y less than delta implies fx minus, I'll use double arrow, implies fx minus xy is less than epsilon. So that is how continuity is rigorously defined. And as you can see, here you have three different quantifiers back to back. So this is an example of a nesting of quantifiers. I'm just going to jump right into examples because understanding examples is the way to understand nested quantifiers. And we will restrict our attention to two levels of nesting. And the meaning for this will become clear in a moment. Okay, so the first simplest example is there exists. Let's say the domain of x and y is, of both x and y, is real numbers. Okay, so now back to the quantifier expression. We'll read it from the left to right. So this will read as there exists x such that there exists a y such that y is equal to 1. There exists x and y such that x plus y is equal to 1. And here the domain is real numbers, so I should put that in here. There exists x and y, real numbers, such that x plus y equal to 1. So when you have two there exists, all it is saying is you just put there exists and then each of the variable. And is this statement true? Well, do there exist variables x and y such that x plus y equals 1? Yes. And we don't need to have a unique solution. We just need some solutions. For example, half works. So half plus half is 1. Also, 0 plus 1 equals 1. So I can put x equals to half, y equals to half makes this statement true. Or similarly, x equals to 0, y equals to 1 makes this statement true. And there are infinitely many possible answers. Hence, the truth value is true. The next thing we want to do is for all. When you have for all x, for all y, x plus y is equal to 1. I'll just combine the two together and I'll say for all x, y. Oh, I need to give you the domain. Suppose the domain is again real numbers. Reals. X plus y is 1. So that's what that statement reads as: for all x, y, real numbers, x plus y is 1. Is this true? It's not true for all real numbers, right? Because I can come up with a counter example. There are many counter examples. Let's take x equals 1, y equals 1. And if I do 1 plus 1, it is not equal to 1. Okay, so when you have multiple for alls next to each other, it just says for all the variables combined together. So for all, and there exists are nice. Now we come to the hard ones. And this is really this is next level of, you really have to put a lot of mental energy to do this properly. So please take your time to do what comes next. The next is for all x, there exists a y. So is that something? Okay, so you have a for all, and then there exists, and then some proposition. And let's put the domain as reals again. Now this is read as from left to right for all x, there exists a y such that x plus y is equal to 1. And here the order is very important. You firstly cannot merge the for all and there exists because there is no combined quantifier. Secondly, the x comes first and the y comes next. The book gives a very nice way of thinking about this. So the way you think about this is like a two-person game. So the first person playing the game is the first quantifier, and the second person playing the game is the second quantifier. So here we have a universal quantifier, and here we have an existential quantifier. So what's happening is the first player picks up the variable value. So here it's universal, so you can pick any x. Now the second variable, the second person has to pick is existential. So they have to pick one possible solution for that chosen value of x. And instead of writing too many things, I'm going to write it like this. Pick an arbitrary x. For this x, can you find y? Such that x plus y equals 1. Is this statement true? So first I'm saying pick an arbitrary x. So let x be an arbitrary real number. Now for this x, does there exist a y? Such that x plus y is equal to 1. And the answer is yes. I can let y be equals to 1 minus x. Y depends on x, that's okay, because y comes after x. And x was completely arbitrary. So for that x, this y works. And so the truth value of the original statement is true. Okay, let's do the last one, which is there exists x such that for all y, x plus y equals 1. And again, let me put the domain on reals. Now we read this as there exists an x such that for all y, x plus y equals 1. So now we're asking, does there exist one x that works for every y? And because x comes before y, x cannot depend on y. So that this one x has to work for all possible values of y. And let's check. So the thing is, here you have to come up with an x just out of the blue, one that works for every y. So does there exist? Now we're coming back to our original problem. Does there exist an x such that for every y, x plus y equals 1. So if I try to simplify this, this is same as saying that x is equal to 1 minus y. Now what's happening is I'm not able to find one x that works for every y. There is, for different y's, there are different x's, but I need to have one that works for everyone. So here, the answer is no. X depends on y. Let me just say that there exists x such that for all y and so on is the hardest of the four. And it's very non-intuitive. Remember that there exists doesn't mean that there exists exactly one. But here it's saying that there exists x that works for everything that comes after it. So there could be more than one x that does the job for you. But that x has to work for everything that comes after. It's very, you have to really stress your brain muscle to understand this. Let me do one more example of this. And it's okay if you don't get this first time. This is hard. This is the hardest part of predicate logic. And in fact, hardest part of most of elementary mathematics. So take your time. So let's say there exists an x such that for all y, x is bigger than or equal to y. And now let me put the domain as natural numbers. And just as a convention, natural numbers for us will start with 0. Okay. Now let's parse this. So what I'm asking is, does there exist? Oops, let me change the problem slightly. X less than or equal to y. Does there exist a single x natural number such that for every natural number y, x is less than or equal to y? It's just asking, is there a smallest natural number? So this is the mathematical way of asking whether a set has the smallest element, by saying there exists x such that for all y in that set, x is less than or equal to y. And the answer is yes. 0 is the smallest element, and so the statement is true. So we need two quantifiers to describe smallest. Similarly, you can try to describe largest, and so on. Okay, so that is nested quantifiers. Now, just one last thing in the book. This is not that common in mathematics, but we are doing it as a mental exercise. It's hard to do for all there exists for large domains. So let us instead do this when the domain is very small. So in this question, we have a proposition P, which depends on two variables, x and y. This coordinate is x and this coordinate is y. And the domain is just 1, 2, 3. So both x and y can take values 1, 2, 3. And what this table is showing is exactly the truth values for that. For example, this entry is P of 3, comma 2. Let's do for all x, for all y, pxy. There exists x, there exists y, such that pxy. There exists, let me do for all first, for all x, there exists y, such that pxy. And there exists x for all y. Okay, so now we're trying to determine truth values of these 4 statements. Let's start with the first one. The first one saying that for all x and y, pxy is true. This is easy. It's literally asking you to look at the truth table and seeing if all of the entries are true, and clearly not. There are some entries that are false and some entries that are true. And so this is false. Now the second one is asking, does there exist at least one x and y such that pxy is true? And yeah, there are many of them such that pxy is true. Oh, by the way, the first one, you can say the counter example is, let's say x is equal to 2 and y is equal to 1. All right, now does there exist one x and y? Yeah, true. There are many x and y, including 1. Okay, now the third one. For all x, does there exist a y such that pxy is true? So what we're doing is we're varying the x first. So pick an arbitrary x. X can be 1, x can be 2, x can be 3. So x can be 1, or x can be 2, and x can be 3. So when x is 1, I'm looking at the first column, and I'm asking, in this column, does there exist a y such that pxy is true? And the answer is yes, there exists one y such that pxy is true. So here we get true. Now when x is 2, I'm asking, does there exist something in the second column which makes pxy true? So the answer is yes. And does there exist a y in the third column such that pxy is true? Again, the answer is true. And let me just mark things. So for example, in the first x equals 1, I'm looking at the first column, so I could have picked y equals 1. For x equals 2, I'm looking at the second column, and I could have picked y equals 3. And for the third one, I could have picked, again, y equals 1. Okay, so for all x separately, there exists the y. The y can depend on the x. So for the x equals 1, I got y equals 1. For x equals 2, I got y equals 3. Okay, now we come to the hardest one. Now we're asking, does there exist one x that works for every single y? And this x cannot depend on the y. So either I have x equals 1 that works, or x equals 2 works, or x equals 3 works. Let's check. So I have 3 possible x's. Does x equals 1 work? What does that mean? I want when x is 1, every y gives me true. Let's see. So when x is 1, every single y value needs to be true, and that is in fact true. So, and the y cannot depend on x. And here I get true. And I don't need to check further ones because I just need a 1x. The whole proposition becomes true. This is also true. Just for the sake of understanding, let's look at what happens when x equals to 2. When x is 2, I want every y value to give me true. But when y is 1, I get false. So here I get false. When x equals 3, again, I want every y value to give me true. But here, again, y equals 3 gives me false. This is not working because of y equals 1. And this is not working because of y equals 3. Okay, so these two don't work, but x equals to 1 does work, and I just needed 1x, and so the whole statement becomes true. Yeah, so nested quantifiers are hard, but that's okay. If you take your time and make sure, don't rush anything, follow all the definitions and the procedure carefully, and you'll get it.